in chemical kinetics, we are dealing the rate of the reactions in terms of zero order, in terms of first order, and in terms of the pseudo first order. There are 2 moles of hydrogen iodide and they decomposes to give what? Hydrogen and iodine. So the molecularity will become 2. These reaction, even though it is not a first order reaction, it is behaving like a first order. Hence it is named as what? Pseudo first order reaction. Hello my dear students, a warm welcome you all. Myself is Purnima, lecturer in Department of Chemistry at Vidhyaashram Pre-University College, Temple of Excellence, Mysuru. My dear students, today we are going to do with the revision part of the unit 4 chemical kinetics. Let us see what is chemical kinetics and what are the importance of this unit and what we are going to understand in this unit. So as we already know that chemical kinetics is a branch of chemistry which deals with the study of rate of the reaction, which indicates that whenever you consider any reaction in chemistry, which means that a reactant, if it is given to the product, okay, on what rate this reactant is converted into the product, we are going to understand in the chemical kinetics. Remember, in the chemical kinetics, we are dealing the rate of the reactions in terms of zero order, in terms of first order, and in terms of the pseudo first order. Okay, there are different types of the integration that we do in order to understand the rate of first order reaction as well as for the zero order reaction and the factors which are affecting on it, which means to say that whenever the reactant is converted into product, when we find out the rate of the reaction for this first order or for the zero order or for the second order reaction, which are the factors which affect for the reactions to happen, that is also we are going to deal with the chemical kinetics. And also the mechanism by which reactions are proceed. So here we are going to learn mainly about the collision theory, which explain that how the reaction mechanism will take place in the chemical kinetics. Okay, this is how we know. Just in the unit 4 chemical kinetics, we are going to understand the rate of the reaction for the zero order, first order as well as for the second order goes on. Okay, so up to the first order you have a integration part to learn and also with the theories and the factors which are affecting on it and a half-life period for the zero order and the first order also, which is there for your syllabus for your second PUC board exam. Let us see the weightage of this unit. So from this unit, we can expect 11 marks. There is a 1 mark question, that is a question number 5, and there are 2 5-mark question. Okay, in this 5-mark question, that is a question number 39 and 40. Definitely one question which is mainly from integration. Integration of what? Zero order or first order. And also we can expect one numerical in this part and also we can expect the differences between the order and the molecularity of the reaction, or we can expect any theories, okay, or the mechanism or a half-life period, which is another important part in the 3-mark question can be asked in this unit. Let us see the 1 mark as well as the 2 mark and the 3-mark question which comes under the 5 mark. Okay, let us discuss with the 1 mark question now. So as I said, this is a unit which is based upon the rate of the reaction, they can give the question like this. For the reaction 2 hydrogen iodide, which gives the iodine and a hydrogen, write the molecularity of a reaction. So already in my concept class, I have explained that molecularity of a reaction, okay. So according to the molecularity, it tells about how many number of reactant molecules are decomposed to form a product. So here you can see that the molecularity of this reactant is nothing but a 2. There are 2 moles of hydrogen iodide and they decomposes to give what? Hydrogen and iodine. So the molecularity will become 2. Okay. Next, what happens to the half-life period of first order reaction if the initial concentration of the reactant is increased. So what will happen to the half-life period of a reaction? For first order, we are talking, if the concentration of the reactant is increased, actually it remains constant because half-life of the reaction for the first order, which is independent upon the initial concentration of the reactant. You will learn what is this actually while deriving with the half-life period for the first order, or they can give you an exam as show that initial concentration of the reactant is independent upon the concentration of the reactant. Okay, they can ask you in this manner also. So this indicates that the half-life of a first order reaction which are independent upon the nature of the concentration of the reactant. Okay, mention any two factors which are influences rate of the reaction. As I said, we are learning about the factor which also depends upon the rate of the reaction. One is temperature and the one is concentration of the reactant. How much the concentration of the reactant is taken to happen a reaction, and what are the conditions that you are maintaining, especially we are dealing with the temperature. So the temperature is very, very important here. Next, what is the SI unit for zero order reaction? Already in my concept class, I have shown that how to write the SI unit for the zero order, first order, second order. It goes like that. Okay. This unit determination is also very simple and it is nothing but mole per liter per second. Next, a chemical reaction has a rate expression. Rate is equal to A square into concentration of the B. What is the overall order? You can see that the concentration of the reactant is 2. Similarly, the concentration of the reactant B is 1. Nothing is there in the sense which indicates that 1. The concentration of the reactant B is 1. So, if you add 2 plus 1, it is 3. So, the answer is 3. Clear? We know that orders are obtained by counting the sum of the powers of concentration of terms which are involved in reaction. Especially in the reactant side we are considering. Okay. The rate of the reaction A is given raised to B, which increases 2 times by increasing the concentration of A by 4 times. What is the order of the reaction? Remember, A is going to give B, okay, increases 2 times by increasing the concentration of the B by 4 times. So, here they have mentioning that concentration of the B is 4 times and it's going to form a reactant which is in the concentration by 2 by 4. Okay. So, 2 ones are 2 twos are 1 by 2 which is nothing but 0.5. Okay. This is how we can calculate the rate of the reaction to show that what is the order of the reaction also. Next, we will see with the 2 more questions which are frequently asked from this unit. What is zero order reaction? Give an example. The reaction in which rate is independent on the concentration of the reactant which is said to be what? Zero order reaction. Example, ammonia in presence of the platinum as a catalyst which decomposes to give nitrogen gas and a hydrogen gas. This decomposition of ammonia into hydrogen where the concentration of the reactant which is independent upon the rate of the reaction, if you write which is become independent upon the concentration of the reactant, hence it is said to be zero order reaction. Okay. Next, what is meant by pseudo first order reaction? Remember, first order is different from the pseudo first order. Okay. Whenever we say the pseudo first order reaction, remember pseudo means false. Okay. These reaction, even though it is not a first order reaction, it is behaving like a first order. Hence it is named as what? Pseudo first order reaction. Okay. The higher order reaction can be converted into first order by changing the experimental condition. Such reactions are said to be pseudo first order reaction. You can take the example of inversion of sugar, where I have considered the sugar cane or cane sugar which is upon hydrolysis, it gives rise to the glucose and fructose. Okay, where you can see that this is not actually the first order reaction but it behaving like a first order. Hence it is known as what? pseudo first order reaction. Okay. Next, give two differences between order and molecularity. This question can also be asked for 3 marks also. Okay. So, if it is asked for 3 marks, 3 differences you have to write. If they ask you to write for 2 marks, 2 differences at least you have to write. Let us understand once again with the order and molecularity. As I already explained that orders are obtained by counting number of sums of or sum of the powers of concentration terms of the reactant in the rate equation. Okay, it is the sum of powers of concentration terms in the rate equation or in the rate expression, or in the molecularity you can define it as number of reacting species that are taking part in the elementary reaction. Okay, and remember your order can be a fraction but your molecularity should be a whole number, and you can expect the order to be experimentally determined but the molecularity will be theoretically it can be determined. Next, define half-life period of a reaction. So, it is generally denoted as what? T half. Okay. It is nothing but time required to convert half of the reactant into a product. It is called as what? Half-life period of the reaction. Next, we will move on to the 3-mark question. It is very important to understand that how to integrate or how to derive integrated rate equation for the 0 order or for the first order. It is a definite question for your board exam. Okay, please understand how do we derive it. Derive the integrated rate equation for the first order reaction. For the first order reaction, we already know that rate of the reaction is directly proportional to the first power of concentration of the reactant. I'll consider the simplest equation where my reactant is going to form a product. Now, for this equation, as I consider A is equal to B, or you can say reactant is going to form a product, where the reactant is going to form a product, you can write the rate equation as rate is equal to D into concentration of R divided by dt. Why I have mentioned the minus D? We know that during the formation of the product, what will happen? The reactant concentration is going to be decreased, whereas the concentration of the product will be increased. Correct? So that is why we will write the minus sign for that into concentration of K into concentration of R. Now, if I rearrange this equation, the above equation, okay, that is dr by dt can also be written as just by interexchanging this. So, dt, so if I arrange this, if I take it into the r outside, so dr divided by d into t is equal to k into dt. Now, for this above equation, if you integrate on both the side, integration of dr divided by concentration of R into K into integration of dt. So, remember the integration of dr divided by R, which is nothing but ln R, and we know that K is a constant, integration of dt is nothing but a t plus integration constant is I. Okay, this is my first equation. Now, I will consider a condition that when time t is equal to 0, okay, and the concentration of the reactant is also considered as the initial concentration of the reactant, what will happen to the equation 1? What will happen? The ln R naught, which is equal to K into 0 plus I. Okay, K into 0 means 0 only. So, ln R naught, which is equal to I. This is my second equation. Now, I substitute the I to the first equation. So, I can write that equation also as, what is my equation? Ln R, which is equal to KT plus I. What is I got now? Ln R naught. Ln into concentration of R naught. Now, I can write ln into concentration of R is equal to KT plus ln into concentration of the reactant at an initial state. Okay. Now, I'll take out this KT outside. Okay. KT outside. What is remaining? we have ln R naught minus ln R. Okay. Now I'll keep the K as such and I can write ln R naught minus ln into concentration of R divided by T. Now if you convert this ln into log, I have to multiply it with 2.303. So I can write K is equal to 2.303 into log of divided by T into log of concentration of the reactant at the initial stage divided by concentration of the reactant. This is a final equation which I have derived in the first order reaction. So, hope you all understood with the simplest integration part for the chemical kinetics. Next, we have derived an integrated rate equation for the zero order. Already we have understood that what is mean by zero order. In the zero order, the rate of the reaction which has become independent upon the concentration of the reactant. So that I will consider the reaction A is going to form a product. If I write the rate equation again, concentration of the reactant is going to be decreased during the formation of the product. So it should be mentioned as minus. So rate is equal to minus into d divided by dt is equal to k into R naught. Now what I'll do the same thing as I derived in the first order. Okay, I'll write the rate equation first. Minus dr divided by dt is equal to k into concentration of R naught. Okay, concentration of R. We know that it is 0. Why it is 0? Because it is nothing but zero order. So the concentration of the reactant to raise to their power is 0. Anything to raise to the power is 0 in the sense it is nothing but 1. So I can rearrange this equation as dr divided by dt is equal to k. Correct? Is equal to k. Now if you integrate for this reaction, integration of minus dr is equal to k into integration of dt. Integration of dr is nothing but concentration of R is equal to k into t plus I. Correct? This is the equation which I have got, and a minus sign which I have taken into other side. I will write it as minus k into t. Now what will happen. I will consider the condition that when T is equal to 0, what will happen to the concentration of the reactant will become concentration of the reactant at initial stage. So, R naught which is equal to I. This is my first equation. This is my second equation now. I substitute to the first equation, okay, as I got here. So, what is my first equation? Concentration of the R is equal to minus KT plus I. What is I now? I is nothing but concentration of R naught. Correct? No? Now, I will take the KT outside. It will become a plus KT. Okay? So, concentration of R naught minus concentration of R. So, I can keep this as concentration of R naught minus concentration of the R divided by T. This is for a zero order reaction. Next, derive an expression for the half-life period for the first order reaction and show that the half-life of first order reaction is independent upon the initial concentration of the reactant. They can ask you directly with derive a half-life of a first order reaction or show that the initial concentration of the reactant is independent upon the concentration of the reactant. They can ask like this. Okay. So let us see how to derive for the half-life of a first order reaction. So let us consider the final first order reaction for this. Okay. And I know that T is nothing but T half here because it is a half-life of a first order reaction. So I can consider the T as T half and the concentration of R, that is a concentration of the reactant is nothing but initial concentration of the reactant divided by 2. Because we know that in the half-life period, it is nothing but time is required to convert half of the concentration of the initial concentration of the reactant. That is why I divided by 2. Now, I replace the rearrangement to the above equation. What will happen? So, K is equal to 2.303 divided by T half into log of R naught divided by concentration of R0 divided by 2. Okay. So now I just rearrange this. T half, which is equal to 2.303 into K into log of R0 will get cancels. Log of 2 you will get it, correct? Log 2 is nothing but 0.3010. So I can write here half is equal to 2.303 into 0.3010 divided by K. So if you multiply this, you will get T half is equal to 0.693 divided by K. This is a T half value. Next, we have derive an expression for the half-life of a zero-order reaction, or they can ask you like this. Half-life of a zero-order reaction is directly proportional to the initial concentration of the reactant. So, I'll consider the final integrated rate equation of the zero order. As I said, when I say it is a half-life period, T will be equal to T half and the concentration of the R will be equal to R0 divided by 2. Okay, so the rate of the reaction will become, what will happen? K is equal to R0 minus half into R0 divided by T half, so that I can take the R0 as constant. So K is equal to R0 divided by 2K. Okay, when it is multiplied. So this is a final equation which I got for the zero order reaction. Lastly, we have a certain first order reaction is 75% completed in the 30 minutes. Calculate the rate constant they have given, and also they have mentioned that it is a first order. So first order in the sense we have a equation that is K is equal to 2.303 divided by T into log of initial concentration of the reactant divided by concentration of the reactant. In the equation only they have given that first order reaction is completed, 75% is completed. So now I consider the initial concentration of the reactant as R. Okay, so the concentration of the R is obtained by 100 minus 75 as they have mentioned, which is equal to how much? 25. Correct? And also the T is given, which is nothing but 30 minutes. Now I substitute for the above equation. 2.303 divided by 30 into log of 100 divided by 25. Okay, so how much you'll get it? If you divide a log of 100 divided by 25, and if you find out the log value for that, you will get 0.6021. 0.6021. Now if you multiply 2.303 into 0.6021 divided by 30, 0.04322 per minute. Why? They have expressed the rate constant in terms of minute. Okay, this is how we know the rate constant for the given reaction can be easily calculated just by looking at with the data and also by remembering the formula for the zero order as well as for the first order. Most of the time the numericals can also be expected on zero order, or we can expect on the half-life period. Okay, so we can expect the reaction like this. So finally, we can derive like this. Hope you all understood with this session. I'll come back with the one more unit. Till that, take care, be safe. Thank you.